Hi, my name is Unique Handale. I'm a PhD student in the Mechanical Engineering Department of the University of Texas at Arlington. Today, I'm presenting a topic, a computational approach to study the impact of PCB thickness on QFN assembly under drop testing with the package power supply. One of the critical challenges in the electronics is a drop impact failure. As our device gets smaller and more handier, like they become more exposed to damage from everyday drops. Think about your phone. It's constantly at a risk. So our research focuses on understanding how to make this device more reliable. We are not just looking at the impact itself, but also assessing the behavior of a drop to the stress. We are specifically looking at the QFN packages, which are these small, efficient components you will find in many devices or circuit boards. Whenever you pick a circuit board, there's a very, very high probability you will see this kind of package. We'll see how the stiffness of the circuit board, their mounted, plays a role in determining the solder joint reliability. So for the objective, repeating one more time that our main goal here is to figure out how the design of a circuit board influences the reliability of a solder joint when a device is dropped. And then we are trying to move beyond a simple drop test and creating a more accurate picture. When a device is dropped, like a phone, it is not just a pure mechanical impact or a drop. When a phone is being used, it's dissipating heat. Therefore, we are combining the thermal and a drop together to better estimate the effect and better estimate the reliability and risk of it. We also rely on the testing method for material characterization of the PCB. PCB is unique as per the application and circuit design. This shows orthotropic property, and it is critical that we use the right property in all three directions. To measure the properties, we have used thermal mechanical analyzer machine for the coefficient of thermal expansion metric, and then a dynamic mechanical analyzer for elastic modulus. These properties were measured are temperature dependent because we will be like looping the thermal load as well. And then we have measured it on two different PCB thickness, which we will be comparing at the end. Once the properties are measured through the machine, we'll jump to the simulation part of it. We built a model to simulate the drop test. The model includes the heat generation by the component that we have done by applying a power to it. We set up the model to mimic the real world condition, like how the board is attached to the device. We then ran simulation to see how the board bends and how much stress that puts on the solder joints. The key takeaway here is that we are looking at what happens when you combine the impact and the heat. The device experiences this heat. As a result discussion, what we found is that stresses on the solder joint don't just appear instantly during the impact, like one single cycle, but they actually oscillate or vibrate for a short period, similar to how a shock is being happen and then it fades out with a small time. And as you can see in the plot, when the device is powered on and generating heat, the stresses are different, higher compared to unpowered state. This is like a very good finding that it is critical to have account this higher stress because of the heat. We also saw that the thinner, more flexible board tend to bend more, which puts a different kind of stress on the solder, a peeling stress. But a stiffer board, while bending less, creates a higher constraint on the board, indirectly influencing the solder joint stresses, which is the link between the package and the board. So to wrap up, in the summary, we carefully measure the circuit board properties, and then we use the data to create the computer simulation model. We found that the heat dissipation significantly increases the stress on the solder joint during a drop, and then stiffer boards tends to put more direct stress on the solder joint, while the thinner board have a more tendency of bending, resulting into a peeling stress. This means that the design reliable devices, we really need to consider both mechanical impact and then the heat generation of a device to better estimate the risk of drop impact. At the end, I'd like to thank my professor, Dr. Derek Jagnaufer, and the member of EM and SPC for continuous support and guidance. Thank you so much.